Okay, hello again. So, Euler entered the field or entered the scene in 18th century. Then he actually contributed a lot to calculus of variations. So, Euler got interested in what are called now geodesic curves. Okay. Geodesic curves are the least distance curves on any given surface. In a plane, if we are given 2 points A and B, the least distance curve is straight line, because straight line is the least distance to go from point A to point B. On the other hand, if you are on the surface of a sphere such as the one shown here, if you have a point over here and a point there, then straight line cannot be drawn on a sphere, right. So, it has to be a curve that can be drawn on the sphere. It turns out that the curve that will give you the least distance on a sphere will be arc of a great circle that will be passing through the two given points A and B. Okay. Such things are called geodesic curves. Geodesic curves are the curves that give you the least distance paths on any given surface. Whatever surface you take, can be a highly uneven surface or a hyperboloid or any surface you take. If you are given 2 points, if you find a path that takes the least distance to go from point A to point B, that is a geodesic. Okay. The geodesic is something that civil engineers use even till today. If you want to lay a road between two cities or two places, they have to look at the ups and downs of the terrain and find the road that will be the least distance following all the ups and downs. Okay. So, the geodesic. So, Euler got interested in these and started solving those problems and others, and there was general theory for calculus of variations. Okay. Basically, these curves and surfaces have a lot of relation with the mechanics also. In the middle of 18th century, lot of other people, some of the names are given here including Euler, Mathematicians, Leibniz, and Leibniz we already found in the context of Brachistochrone problem, and Lagrange. All these people had started looking at geometry of curves and surfaces and applied that to the mechanics to develop some integrals, something is called an action integral and other ways of looking at mechanics, and they try to look at the minimization, Gaussian minimization in all of these problems, which when you try to minimize and find a condition that will lead to a differential equation, okay, to solve for the unknown function. So, unknown function is the cornerstone of calculus of variations, right. So, that as the unknown function, you need when you have an unknown function, the equation that enables you to solve that is a differential equation. And the differential equation comes out as a necessary condition or a condition for the minimum of a functional or an integral kind of thing that we have seen in the last slide. Okay. So, this is known as Euler Lagrange equation. Okay. He developed this equation for the geodesics and other things, Euler. Okay. We will understand what f is and what this actually means later on. For now, let us recognize that there is something called a Euler equation, but also the equation is known as Euler Lagrange equation, because Lagrange, who came after Euler, but of course they were contemporaries for some time, and he was 20 years old when Euler came to know that this young man Lagrange had solved the problem that he had solved and derived the same equation, but in a different way, and Euler thought that Lagrange's method was more elegant, and in fact Lagrange had used the concept of what we today call variation, and Euler liked it so much for the elegance of the solution, and he said, do not take my method, take Lagrange's method instead, which is what we adopt today, but the equation that we had put in the previous slide is still known as Euler Lagrange equation. Okay. It can solve minimum surface problem, minimum curve problems, and many things in mechanics and other fields. And one of the things with regard to surfaces is the soap films, which we will see in the next lecture, how soap films take the minimum surface given the amount of soap film that is available to them, and basically they want to minimize the surface energy. Okay. But also it turns out to be minimum surface problem, and we will look at all of those things in the next lecture. Okay. So, Lagrange introduced this concept of variation to this field of calculus of variations. Now is the time for us to understand what variation means. Okay. Let us say we have a curve such as the one that is shown here in solid, another curve which is shown in dashed red line, which is a perturbation of the original curve. Here for clarity I have shown the perturbations a lot, that is if there is this solid curve, right, let us say it is perturbed, like imagine it is a string, somebody has perturbed it, starts vibrating, right, then it becomes something like this, and that is the variation. So, you have a curve and you have perturbed it a little bit, so it deviates from the curve in some fashion, deviation can be very small, something like this also, right. So, that is the variated curve or a curve plus variation. Okay. When you do that, this gives rise to the notion of local minimum. When do you say a particular curve, let us say I have a curve like that, when do I say this curve minimizes something? I say it when if I consider small perturbations around this curve such as those, if this perturbed curve is substituted into that function or objective that we have, then the amount of the magnitude of that value of that functional or a integral will be higher than what it is for the original curve. So, for all the perturbed curves, the value of the functional should be higher than it is for the original curve, that should be greater than the value that is there, okay. In which case we call that curve a local minimum, okay. So, that is why variation concept, which is the perturbation, which is a very important concept in calculus of variations, it was introduced by Lagrange, okay. Later on after this Euler Lagrange looked at the necessary condition, Jacobi and Legendre and others considered the sufficient condition also, okay. And so, while Euler Lagrange equations give you the necessary conditions, the Jacobi condition and Legendre condition, they give you sufficient conditions for this. In between, another person, a Russian mathematician Mikhail Ostrogradsky, also contributed calculus of variations. If you look at some of the Russian books now, they actually call them Euler, Lagrange and Ostrogradsky equations. So, optimization problems always have necessary and sufficient conditions. It is important to understand what they mean. In fact, they do not mean anything more than what they say. Necessary conditions are necessary, that is absolutely needed, and sufficient conditions are sufficient. Basically, the two words say what they mean. Necessary conditions may not be sufficient or not sufficient, and sufficient conditions are not necessary. Sometimes you can have some conditions which are necessary and sufficient, okay. These are important words, but you do not have to worry about them because they basically say what they mean. Necessary means it is necessary, sufficient means it is sufficient, okay. So, Euler Lagrange had dealt with the necessary conditions and other people had dealt with the sufficient conditions. That is another development in the field of calculus of variations, okay. And much later, so there is a person named Bois-Reymond, he had a fundamental contribution which is called the fundamental lemma of calculus of variations, which many people had assumed, as we will see later on, but he had proved it rigorously, and that is the fundamental lemma. So, lemma is something that is slightly less in status as compared to a theorem, and that is what this Bois-Reymond had proved, okay. This fundamental lemma of calculus of variations is actually very simple. Let us say that you have a function f of x, if the integral of f of x from a to b multiplied by h x. So, the integrand now is f of x and h of x dx equal to 0, and this h x is arbitrary, like our variation, it can be any perturbation, okay. So, when h of a, h of b equal to 0, they are the boundary conditions, okay. These are the boundary conditions, these are called end conditions or boundary conditions, okay. If this is equal to 0 for any h, so h is arbitrary, then what the fundamental lemma says is that f of x equal to 0 for the entire interval a to b including the ends. Okay. That is the fundamental lemma, which is intuitively very clear. If you are integrating a function with an arbitrary function, for any arbitrary function the integral has to be 0. If f of x is 0 identically for all values a to b, then this is the fundamental lemma, which is intuitively clear, but he had proved it rigorously. We will use this fundamental lemma when we derive the Euler-Lagrange equations later in the course. Okay. Much later, when it comes to mechanics or what we call variational methods, Hamilton, Riemann, Dirichlet, Weierstrass, a number of other researchers had applied calculus variations to mechanics and derived wonderful energy methods or variational methods for mechanics. And at the same time, Pontryagin much later in 20th century, he developed the optimal control theory that is also related to the calculus of variations. And Richard Feynman, the Nobel laureate, are famous for his physics lectures. He used calculus variations in electrodynamics. Before that, Schrodinger had used calculus variations in deriving what we now call Schrodinger's equation, and economists, writers, philosophers, a lot of other people also use the concept of minimality. Even if it is not calculus variation, there is a notion of minimality in all of these things. Everybody uses some way of minimizing, like we said in the last lecture. In life we try to optimize things or minimize. So, that is calculus variations. If you know, you will have a powerful tool which is a foundation for many mathematical physics concepts. Okay. Just to summarize what we have discussed today, if you look at historically from ancient time BC, there was the isoperimetric problem, and then the Fermat's conjecture about refraction of light, that is light rays taking minimum distance path, and then the classical problem of Brachistochrone, which is a very important one that was in the end of the 17th century, and then Euler and Lagrange derived, and Ostrogorodski also contributed to necessary conditions, and Legendre, Jacobi and others did the sufficient conditions, and the fundamental lemma was proved by Bois-Reymond in the 19th century, and 20th century used calculus of variations in mechanics heavily by all the people that are listed. Optimal control theory has it, and quantum electrodynamics and Schrodinger's equation, all of these use calculus of variations. So, it is a very important tool. Today we discussed the history of calculus of variations, and in the next lecture we will discuss some of the problems in geometry as well as mechanics. Thank you.